Buenos tardes. Buenos tardes. Gracias por invitarme a hablar a RubyConf Colombia. Yo no hablo español, como se puede ver. Con su permiso, voy a hablar inglés. Gracias por invitado. Thank you for inviting me. Thank you for inviting me. One of the things I've loved about RubyConf Colombia so far is that everyone is so outgoing and friendly. I've bothered many of you who happen to speak both Spanish and English. I've said, como se dice this, como se dice that, to try to acquire some vocabulary so that I might communicate more effectively with you. And I thank you for being such wonderful. The word I learned was profesores. So thank you very much for all that you've shared with me. And I pray that I'll be able to share a little bit with you also. So thank you for the invitation, and thank you for the experience here in Colombia. First time in South America, so thank you for all of that. Let's talk about supercomputers. Specifically, we're going to talk about a supercomputer called a Parallella. This is a Parallella, and you can see it in my hand in this photograph. It's about the size of a Raspberry Pi or a credit card. It has 18 cores, 2 of them are ARM, 16 are RISC, and we'll talk about those definitions a little bit further on into the talk. And you can buy this thing online for about $150 US on Amazon. So that's Parallella. When we get into the talk, as we move forward in the talk, what we're going to discuss is why you care about parallel computing, why you care about supercomputing, and what it means and what you can do with it. My name is Ray Hightower. I run a software company called Wisdom Group, and together my team and I, we run the Chicago Ruby User Group and a couple of conferences. We run Windy City Rails in Chicago and Ruby Carib in the Caribbean. We first became interested in supercomputing, and when I think of supercomputing, I think of big room-sized computers like a Cray XMP from back in the day or an IBM Blue Gene from the current day. We first became interested in supercomputing at Wisdom Group when we acquired a client that was doing research in supercomputing. This is a team of high-end PhD computer engineers led by Dr. Valerie Taylor at Texas A&M University. And they're doing research on computers that have 100,000 cores or 1 million cores or more. And they're collecting tons of data, mountains of data on power utilization and heat dissipation and performance. And they needed an effective way to sift through all of this data. So they came to Wisdom Group to build a web app for them to sift through this data for them. The metaphor I like to use is, it is as if they are medical researchers researching some of the deadliest diseases ever known to humans. And they came to us to build microscopes. We don't know everything that they're looking at these microscopes. You know, we don't know everything that they're looking at these microscopes at, with their analysis and all of that. But the more we understand about their analysis, the better we can serve them. So that's why we started learning about supercomputing. Now, I'm going to start off by telling you that this talk will focus more on parallelism than concurrency. Concurrency is not parallelism. I thought they were the same, or at least synonyms, kind of like prawns and shrimp or dolphins and porpoises at some point, right? But they're not. And if you want more details on the differences, there's a talk on YouTube by Rob Pike, one of the creators of Go, where he goes into that in more detail. From what I understand and from what I've read about concurrency versus parallelism, I'm going to take a big risk here in a room full of really smart people. I'm going to say what I've learned about concurrency is that concurrency is almost an illusion, in that you can achieve concurrency on a single processor system in this way. Remember back when computers had a single processor, you had a mouse, you're moving it around, and there's video appearing on the screen, and you're typing keys on your keyboard, and all of these things seem to be happening at the same time. But actually, the processor is doing time slices every 20 milliseconds. I think on the old x86 processors, every 20 milliseconds, it would switch to a different task, either listening to the mouse, listening to the keyboard, and every 20 milliseconds, it would shift to a different task, giving the illusion that these things were happening at the same time. So concurrency is an illusion, and I'm grateful to be doing this on video, which may be on the internet at some point, because if there's one thing I enjoy is if I'm wrong, people will correct me publicly and loudly on Twitter, so I'm looking forward to that. But I think concurrency is an illusion. Parallelism, on the other hand, is when you have things happening at the same time on separate processor cores. So we're going to talk more about parallelism. We're not going to talk about concurrency today. And if you'd like to know more, check out Rob Pike's talk. It's a good talk. So coming up next, parallelism is not new. It's something we've thought about for a long time. And as you can see, here's Grace Hopper holding a COBOL manual. So you know how long ago that was, right? I won't read to you Grace Hopper's quote, but the bottom line is, if we want to achieve more processor performance, we're going to do it not by making bigger and bigger processors or trying to push these transistors closer together on a wafer of silicon, but rather we're going to achieve it by building more processors. Not a bigger ox, but more oxen. And why is that? Moore's law. Here's a chart of Moore's law. You're all familiar with it. It is the observation that every 18 months or so, we would be able to double the number of transistors on a wafer of silicon. And we have ridden that free ride about as far as it's going to take us. We are maybe 10 years away from the end of Moore's law. But every year, every 2 years, every 18 months roughly, we've been able to double the number of transistors. One of our interns at Wisdom Group looked at this chart and said, maybe there's a more visual way to express Moore's law. And she found this chart from the Washington Post. Her name is Yvonne Garcia. Yvonne Garcia found this chart that shows Moore's law visually and viscerally. Every function in the photograph at the top is in the signal device on the bottom. That's Moore's law, and that's where it hits you in the gut. That's why we've been able to achieve that. But unless we come up with another way to extract and increase processor performance, we won't be able to make another set of photographs like that in the year 2023 or the year 2033. So let's look at parallelism. And Parallella is this device. You know, we'll talk about speeds and feeds. It's a full-blown computer. You've got RJ45 power, about 5 volts of power, 5 volts at 1 amp, 5 watts, micro USB, micro HDMI, micro SD, which takes the place of the hard drive that you might have on your laptop or a desktop computer, and that's Parallella. This is Parallella inside of a case, and the remarkable thing about this case, and I can show you one of these after this talk if you like. I have one with me in my backpack. This case was designed by Dr. Suzanne Matthews, who's a professor of computer science and computer engineering at West Point. Dr. Matthews is teaching courses on high-performance computing at West Point, and she chose Parallella as the device of choice to introduce her students to this subject. And she and her team created a case to hold the device because it gives off a lot of heat. Cool thing about this case is that it is 3D printable. I'm double-clicking. Okay. We're back. This is where we want to be, actually. The case is 3D printable, and it's stackable like a whole bunch of Legos. So if you go to Thingiverse, which is by the MakerBot people, you can download the plans and print this on your own 3D printer, and you'll have a case for your Parallella that is stackable like Legos. So if you want to go massively parallel with your Parallella, I don't know the limit to the number of those cases you can stack. I guess it depends on how much filament you have in your 3D printer and how long you're willing to wait for those to print, right? So let's take a look. This is the desktop of Parallella when you've got it hooked up with your HDMI monitor and your USB keyboard. You've got a terminal. You've got a browser. But I must tell you, it does not perform exceptionally well as a desktop computer. It's not really what it's designed for. It can function as a desktop computer, and we've done that, but it's much better as a device you might put in an embedded system where you require parallelism. Let's talk about power, watts and dollars. One of the biggest problems that supercomputer engineers face when they're designing these massively parallel systems is power utilization. Electricity is expensive. And the rule of thumb that they use when they're deciding on a design for a supercomputer or for a massively parallel system, the rule of thumb that they use to drop their budget, the money budget for the computer, is that 1 watt used over the course of a year will cost about $1. Or 1,000,000 watts over the course of a year will cost about $1 million. So if you go to top500.org, this is a list of the 500 fastest supercomputers on the planet. The top 3 are right here on this chart. Fastest one is in China right now. If you look real closely, you'll see that it uses 17.8 million watts And over the course of the year, that's $17.8 million. That's a lot of money to be spending on a computer. Yeah, I can see from the looks on your faces, that's a lot of money, right? Even if you're a billionaire, that's a lot of money, right? Parallella uses less wattage. It uses about 5 watts. And one of the tests that I wanted to run, one experiment that I wanted to run to determine how much energy it was actually using is I wanted to create some type of experiment that would show me what it's actually using. So I grabbed one of these devices. You may recognize it. This is a solar panel that you might take with you when you go camping. It's got a solar panel on one side and a lithium-ion battery on the inside. It's about the size of a smartphone. And then grab the cable. If you're like me and you collect electronic devices over the years, the adapters for those devices pile up, especially after the device becomes obsolete, it's out of date, and you toss it out or you give it away to somebody, but you keep the power adapter because just in case, you might need it for something. So, I got a box of those in the back of my closet, right? So I went to my closet, pulled out one that happened to fit in Parallella, grabbed a USB cable because USB cables are starting to become ubiquitous. They're all over the place. And this is the splicing methodology that I use, and I go into more detail on exactly which line gets spliced where and soldered where in my blog at rayhightower.com, and hooked it up to the device, and it works. 5 volts, 1 amp, 5 watts. And for me, that's a visceral representation, a visceral and visual representation of how little power this 18-core Linux running supercomputer uses. That blew me away. So we talked earlier about RISC and ARM. Let's see if I can get it right there. I might go away from the clicker and might use the keyboard, but that's all right. RISC is, many of you already know this in the audience, RISC is reduced instruction set computing. And what RISC is the 80-20 rule applied to computer science or computer engineering. It's the 80-20 rule applied to computer engineering. Specifically, computer engineers have observed that 20% of our instructions are used 80% of the time. So why not make that 20% of our instruction set highly efficient, highly performant, very quick, very efficiently operating, and then build the other 80% of our instructions on top of that 20% set, using that 20% as our building blocks. So that is the theory behind RISC, and we've achieved a lot of performance because of that. ARM is really Advanced RISC Machine or Acorn RISC Machine by a company out of the UK. And ARM is the same company that created the intellectual property that created the chip that's in our iPhones and our iPads today. So Apple, they use ARM's intellectual property. They go to a fabricator like Samsung or TSMC, and they get the ARM chip made. So the Parallella has dual-core ARM, and it's got the 16-core RISC on the board. So there's ARM and there's RISC. Now, we're not going to spend a lot of time on the ARM chip because the fascinating thing about Parallella really is the RISC chip. Here's a schematic of what's going on. As I mentioned, there are 16 RISC cores, 4 rows, 4 columns, all reduced instruction set computing cores, running at 1 gigahertz. Now, another fascinating thing about the RISC architecture here, or the Epiphany architecture, the Epiphany RISC architecture as it is built onto the Parallella, is that the address bus is 12 bits wide. 6 bits for the row, 6 bits for the column. And you may just say to me, well, Ray, if we only have 4 rows and 4 columns, we only need 2 bits for the row and 2 bits for the column. And you're right. There's 4 extra bits for the row, 4 extra bits for the column. What does that mean? That means that the designers of this device have already decided that they will need 6 bits for the row and 6 bits for the column. 2 to the 6th power is 64. They're envisioning a Parallella which would have 64 rows, 64 columns. 64 times 64 is 4,096. So we could see a device like this that would have 4,096 cores in the future. They haven't made an official announcement, but we're engineers, we're studying this, we're looking at the width of the address bus. The room is there, so there's certainly possibility there. Now let's look at some code. First program we're going to look at is called Hello Epiphany is Hello World, essentially. Epiphany is the 16-core RISC chip, 16 RISC chips. And Hello Epiphany is the first program that Dr. Matthews has her students run at West Point. On the Parallella, the the ARM chip, that behaves as a host, and the Epiphany behaves as a coprocessor. So if you're writing programs in parallel, you've got a host component and you've got an Epiphany component. And typically you'll call them host.c and epiphany.c if you're writing them in C. And here we go. Let's take a look at this running. And this is just Hello World. We're going to go ahead and LS, just to show you that you're on it. It runs Linux, by the way, if I did not mention. It runs the Linero distribution of Linux. We built it, we're running it, and all we're doing is we're tapping each of the cores at random. You can see row, comma, column, tapping each core at random and saying, hello world from whatever core we're saying hello world from. So real simple warm-up exercise, just stretching out before we start to run and do something interesting. Prime numbers. We all need prime numbers for encryption. We deal with primes all the time, right? So let's see what it would take to calculate all the primes between 0 and 16 million in serial on the Parallella. Not using the parallel functions of the Parallella, but just in serial. And here's the program that we're using to do that, or a snippet of the program that we're using to do that. And we'll zoom in a little bit closer. As you can see inside of our for loop, we are incrementing by 2 because, of course, if we're looking at prime numbers, we only need to look at the odd numbers. And even numbers never going to be prime, except for the number 2. 2 is prime, but that's the only one. And let's watch this run. And what you see is the program that we just showed you is running on the Parallella in serial, and we've asked it to every 100,000 numbers or so to print out where it is, just so we know that it's not dead, just so that we know that it's alive. And it's going to take a while to run. In fact, I'm not going to let you watch the whole thing. In this brief video, we're going to skip right to the end in a few seconds, and you'll see how long that it took to run. It took 237 seconds to run, 237 seconds, just under 4 minutes. And it found 1,031,130 primes. That was running in Parallella, on the Parallella in serial, just under 4 minutes. Let's take the same program, as you would expect. It's a MacBook Pro. Parallella is about 150 bucks. MacBook Pro costs about $2,000 or what have you. And so it better run faster, right? Or else somebody wants their money back, right? So on the MacBook Pro, looking at all the primes between 0 and 16 million, about 14 seconds. Not too shabby, right? 4 minutes, 14 seconds. What if we run it in parallel on the Parallella? And parallel on the Parallella. Now, a couple of things I'm going to point out. I'm going to stop using the clicker. I'll go ahead and use the keyboard here, because that may be easier for us. Now, I want to point out a couple of things. At the very top, you see that we're including in the C program ehal.h. That is the Epiphany Hardware Abstraction Library. That's the library that we need in order to communicate with the Epiphany chip, which is where we have the 16 RISC cores. So it's a C library. We include that in our C program. And let's make that baby run and see what happens. And here's what's going on. Row and column for the particular core that is running the test. That's the number that's being tested at the time, the number of primes it has found so far, the number it's currently looking at, and the square root of the number it's currently looking at, because you only need to look up to the square root of the number that you're examining. And it ran in just over 18 seconds. So to summarize our results, in serial on the Parallella, it took about 4 minutes. Serial on the Mac, 14 seconds. Parallel on the Parallella, about 18 seconds. You mean to tell me this $150 computer, if we write our programs in parallel, it can perform almost as well as a Mac? Oh, no. Well, don't throw away your Macs, right? Don't throw away your Macs, because this is an example of what computer engineers and software engineers who study parallel programs, this is an example of what we're calling an embarrassingly parallel problem, or an embarrassingly parallel program. It's embarrassingly parallel because the next result is not dependent on the previous result. It's very easy to divide the problem into pieces such that when you divide it up, the result in one piece is not dependent on pieces elsewhere. So it's embarrassingly parallel. And there's some problems that are like that. For example, the Mandelbrot set. Some of you may have studied this. It's really graphics where you're looking at real numbers and imaginary numbers, and you want to see what's going on with those. And Mandelbrot sets are exciting because, I'll let it start running for you in a second. Here it comes. Mandelbrot sets are exciting because all of this is mathematics calculated in real time. This is not a screensaver where it's just showing you photographs, but it's calculating the Mandelbrot set in real time. On the horizontal axis are your real numbers, on your vertical axis are your imaginary numbers, and it's doing all this math right now, and it's splitting it up into pieces so that it can calculate it very quickly. And the MacBook Pro doing this in serial doesn't do it as quickly as that. And Mandelbrot sets are not necessarily practical right now. I like to think that maybe Mandelbrot sets will be practical in something we haven't discovered yet. The example I like to use that's totally ridiculous is warp drive, right? What if Mandelbrot sets are the foundation of warp drive, or maybe closer to what we're studying today, what if they're the foundation of something that we will discover in pharmaceuticals? So that's why they're exciting. Coming a little bit closer back to home, where are some places where parallelism might be practical? Well, consider finite element analysis. Finite element analysis is something that a mechanical engineer or a structural engineer may do in order to examine a body and to determine whether it will break, whether it will wear out, and whether it will work. Consider the object in the back, the rusty object that's part of a pier in the back. You burn that image in your head, and what you do with finite element analysis is you divide that element or divide that object into tiny elements, tiny pieces, and you construct a free body diagram for each of those pieces. And this is something that a lot of us studied in physics. You want to look at all of the forces, the vector sum of all of the forces operating on that body, and when you know how those forces are behaving on that body, you know whether that piece is going to move left or right, up or down, whether the entity as a whole will break, whether it will fall, or whether it will withstand whatever pressure it is undergoing. So these are the pieces that you may break your object into, and you can perform your analysis on it and know in advance, before you design it, before you build it, you will know in advance whether the bridge will stand or whether it will fall. Very useful to know. It reduces the expense of determining up front whether a bridge is going to function for you. Another example where parallelism plays a role is in weather prediction. It's almost the same type of thing. In weather prediction, you divide your map into smaller and smaller cells. The smaller your cells, the more processing. I'll hold this like this. You can hear it okay this way, right? It doesn't look as fancy, but it's more effective, I think. There we go. So you can divide your map into smaller. The smaller the cells, the more accurate your prediction is going to be. But then again, the smaller your cells, the more powerful your processor must be in order to do your weather prediction. Now, where does Ruby play a role? In our case, Ruby helped us to think through the parallel algorithms that we were playing with. We've installed Ruby on Parallella. It doesn't run particularly fast, as you might expect. It's only about as fast as a Raspberry Pi if you're just running the ARMs. But if you're running something that you can divide into parallel tasks, then you can achieve some performance. What we envision is perhaps running Ruby on the front end. Maybe you have a web app or some type of interface that is written in Ruby that's interfacing with humans. And then on the back end, if you have some type of job that needs to be parallelized, that's happening in the parallel on the back end. And this is an ongoing research project for us. So every time I give this talk, I know a little bit more, and I try to share more and more with the audience. For example, we know that Mats is working on something called mRuby, which is an embedded form of Ruby. And stay tuned, because I think we'll see some exciting experiments with mRuby and Parallella coming up. Some of you may ask me, well, what about GPUs? I have a GPU, a graphics processing unit on my laptop that has hundreds of cores. What's the difference between a GPU and a Parallella? You know, why don't I just use the GPU instead of working with Parallella? And you can. You know, in the case of a MacBook Pro, if you go into About This Mac and you drill down, you'll see what type of video card you have on your Mac. And if you Google it and go to NVIDIA or whomever it is that made your video card, in this case, we have 384 cores. But the thing is, a core is not a core. A core on a GPU is not like a core on a Parallella. It's almost like apples and pomegranates. The difference between them is that a GPU core is really a very specialized core designed to, here's an oversimplification, right? In the case of video, it's designed to draw triangles over and over again very quickly. Because a lot of the graphics that you might see in a video game or in an architectural drawing are a lot of the graphics you will see, particularly when you're looking at something in perspective or in 3 dimensions. Those graphics are a triangle or a summation of triangles. So the graphics card is drawing triangles over and over again very quickly. A metaphor I like to use is it's as if you had 2 robots. One is a very specialized robot in a factory that does one thing over and over again versus something like an Asimo by Honda that is more generalized and can even play football. You see that? I said football, not soccer, right? I'm an American, I said football. All right. So we're coming up on the end of the talk right now. Just to summarize, this is Parallella. My team and I became excited about this when we started working with a client that's working on massively parallel systems. This is in no way a massively parallel system, but it's something that we're using to learn more about parallelism so that we can serve this client more effectively. And if you have any interest in doing that as well, I'd encourage you to go get one. They're inexpensive. They're all open source hardware, open source software, and I think you'll enjoy it. Thank you very much for listening.